to get started, just some of the old business items. Oh, actually, I guess before I start, let me ask if there's anything. So we'll talk about a few of these old items here and a couple of new items. Hopefully you can see them all. Are there any other items that anybody wants to suggest that we either address today or in a future meeting?
Just a comment. Good job on the news the other day.
Oh, thank you. That
You guys
was
were awesome.
That was Bradley. He set all that up, and we just smiled and played along. But thank you.
It was all Brad's fault.
Good actor, Matt.
Anyway, there was another segment where Brad actually did some stuff, and they never posted it, and we're not sure why. So it might have been because the news guy was talking about getting high or something, but I don't know. So,
Okay.
anyway, well, thank you for that. We appreciate it. Hopefully, our goal was just to do something for Weatherization Day. We hope that we don't get too many, that you guys aren't getting inundated with calls or anything. We tried to keep that pretty low key. But anyway. All right, well, we'll get started. If you think of something, I'll probably ask the question one more time at the end. So if you think of anything that you'd like discussed in the near future, we'll talk about it at the end, or at any point in time, send me or Wade or anybody an email, and we'll consider adding stuff to the agenda. So just another reminder, we do have an auditor BPI class in November. It's 2 weeks from yesterday. And so there's 4 of you that will be attending. Make sure you got your stuff done. If you have questions on what needs to get done, or if you have any concerns about that, reach out to Wade today. We got to make sure you guys are ready for that class. Did you have something else on that, Wade?
I just wanted to reemphasize, if your prerequisites are not met, you won't be allowed in the class. I've sent out several emails now. I planned on sending another email today. I'll check and see where everyone's at, but I can't make any exceptions for anyone. If your prereqs aren't complete, you won't be allowed in this class.
Yeah, and we have a very high pass rate, and the reason is because we have a very high bar just to get in the class. Like, you are expected to do a lot before you even show up, as many of you know who've already attended. And then my next note, it kind of pertains to the same thing. We're holding our last BPI Order Class in January. That's the last one we have scheduled. We don't anticipate needing to hold that class anymore, basically in the next year or so. So it'll probably be a while before we hold another one. So if I think I spoke about this at the last meeting, but coordinators, if you have anyone on your staff that you want them to be auditor certified, then you need to talk to Wade about getting them on track to make that January class. If there's anybody out there who would like to get auditor certified, you need to have a conversation with your coordinator and find out if they want to, if that would be an opportunity for you. But we hope to have 2 or 3 openings in that class for a couple of people who would like to join us. And if you sign up and get on track, make sure that you are committed to getting all of your prereqs done. To hold that class, it takes a lot of resources. There will be typically 3 or 4 guys from the state or from one of the local agencies there spending their time helping you guys through that class. So make sure you're doing your part so that we can be successful there. Any questions on that before I move on? All right. From our October discussion, there were a couple of unanswered questions that we ended off with. And we looked to DOE to try and help answer some of those questions. I just wanted to give you guys an update on where we're at on that. The first question was that when is a QCI required to send somebody back, and can a QCI fix some stuff? The answer right now is that we have requested an interpretation from DOE. We've gotten a little bit of feedback from them, on that, but we're still, like, they kind of shared what they think the opinion will be, but they haven't actually given us an opinion yet. So we have handed that to DOE, and we're waiting to hear back from them on that. And we're asking for an interpretation because the way that they wrote the rules, it says that a QCI is not allowed to do any work. So we're asking them to interpret what the term work means, and hoping that they'll give us a little bit of wiggle room there, that a QCI could possibly make adjustments to things that have already been installed or something like that. But the next thing was what happens when a crew goes out and determines that they can't perform a measure that's listed on the audit, and then can measures be removed from without rerunning the audit. We actually sent in a variance, or a request for a variance, on the field guides from DOE. Basically what it means is that there's something written in the that SWS stuff, which is what we had to base all of our field guides off of, and we're asking for them to kind of give Utah an excuse letter to say anytime Utah runs into this specific issue, they don't have to follow the SWS. The variance we asked them specifically about was just that 30-inch space rule in crawl spaces, and they rejected our variance, but they rejected it because they feel like if there's less than 30 inches, or they didn't dare say 30 inches, they just said if there's limited space in a crawl space, then there's really no opportunity to install a measure. So they're basically saying, why are you asking us to give you a variance when there's no opportunity to install stuff? And that's exactly what we were asking them to acknowledge, was that there is in fact no opportunity to install stuff. So we will probably have a few other discussions with them on that, but we do have some response in writing about that, and that will probably allow us to move ahead within the next couple of weeks with finalizing this, which was, so we put out some proposed changes to the field guide based on vapor barriers and crawl spaces. We put that out in June, and it's still not finalized. This was part of it, and we had to wait for a few things to happen before we could actually finalize that with DOE. But I think this conversation will allow us to do that. What that means to you guys is this whole 30-inch rule will probably go into effect. I've heard some of you talking about how you're already implementing it, and I feel like I'm okay with that. Just know as you're implementing it, it's not in writing yet. But I just wanted to quickly review what it is that we proposed. This was stuff that we put in front of this group a few months ago for a comment period. The comment period closed. So unless somebody reaches out to me like today or tomorrow based on some of this stuff, we will proceed to try and put this into our actual rules. But the main thing here is this whole 30-inch rule. So it's just quickly to read through it. It says when the majority of the crawl space is 30 inches or taller, but portions of the crawl space are less than 30 inches tall, the vapor barrier should be installed up to the point where the height drops below 30 inches or as far as can be safely installed. And it goes on to say other weatherization measures in the crawl space, such as air sealing and insulating, shall also be installed according to the 30-inch height limitation. And then this next bullet, when the majority of the crawl space is less than 30 inches tall, the vapor barrier and all other weatherization measures in the crawl space should be considered for deferral. So we wrote this policy to allow you guys, when you run into space limitations in crawl spaces, to basically defer or not do weatherization measures in that space, but still go upstairs and do all of the other weatherization measures that you can do. Now you'll note we were very, very specific in the words that we used. The one word I want to make sure everybody understands is the majority. The majority of the crawl space means that more than half of the crawl space is 30 inches tall. If you get under a modular home that was set down on a cinder block foundation and there's some I-beams hanging down, just because there's a couple of I-beams hanging down does not mean that you can't get into that space. Typically there's room to move around those I-beams, and typically you could probably reach under those I-beams and safely install stuff, even though there may be a height limitation just directly under those I-beams. So basically, if the majority of the crawl space has 30 inches of space, and this is from the dirt to the bottom of the floor joist, that's where you're measuring your 30 inches, then you should be trying to work in that space. Now, the whole idea is safety here. We don't want you guys to get into something dangerous. And then also the other thing that we were very careful in the way we wrote is it says where the majority of the crawl space is less than 30 inches tall, that those measures should be considered for deferral. You don't have to defer them. I've talked to some guys that have feel like we could move this number to 24 inches if we really wanted to. The way we wrote this was so that at each agency, if your coordinator feels strongly that they want you to do work and your height limitation should be 24 inches, then they can make that decision and they can put that in writing. But the state standard is 30, and it's really, up to you guys to implement that and follow the guidance of your coordinators. So just wanted to quickly review that. Does anybody have any questions or concerns on that before we move on? And I don't think I reiterated it earlier, but so this is a proposed change to the field guide. So when we do implement this, it will just simply be going in as an appendix to the field guide, if you're wondering where this is going to be. So, all right, I'm hearing no comments on that, so I'll move on. Anyway, so both of those are still kind of in the works, but wanted to give you an update on those. New business, the first one is no more spray glue. Wade, can you speak to that briefly?
Yeah, what we discovered was Ian has been doing air monitoring while they're spraying chemicals in a crawl space, which should be part of your confined safety plan, guys. Anytime you're creating a hazardous environment, you need to be monitoring the air. I've got some information about the air monitoring equipment he's been using. It's about $1,000 to get the setup. You should all have that. I'll send out some emails with that information for those of you who don't. Anyway, it was very interesting. We've been using a spray glue that works really well. The can says it's green and safe and friendly and all this business, but testing discovered that it's extremely dangerous. It depletes oxygen levels to scary low levels. It caused fumes to build up to the explosive limits, so something like an incandescent light bulb or a spark or something could have blown the crawl space up with everyone in it. So based on the testing that Ian discovered, we've decided that that particular spray glue, don't be using it. And the other thing that's really scary is this all occurred while he was using ventilation in the crawl space. And the buildup was rapid and large. So, thank God they were testing and discovered it before someone got injured or killed. So again, when you're using chemicals in a confined space as part of your confined space safety program, which you all should have, you need to be monitoring the air. So for the meantime, don't use that particular spray glue anymore. We've sent out an email. We're looking for alternatives, and we would ask any of you, help us find the alternatives. You guys are the ones out in the field doing the stuff every day. So anything you can come up with to help, that would be great. Ian was going to look at some other ventilation strategies using both pressure and depressurization ventilation, so basically doubling the ventilation to see if that doesn't help. But anytime we're in a situation where we are creating a hazardous environment in a confined space, your confined space policy has to address that, and essentially it becomes a permit required confined space, meaning someone has to be standing guard making sure that no one accidentally enters that space, making sure that if something bad happens, you've got a rescue plan in place. So be aware of that. Anytime you're using chemicals in a confined space, you need to be monitoring the air in that space as part of your confined safety plan.
Wade, what kind of help are we offering if they don't really know how to do this?
Call us and we'll work with you. We'll help you with get your hands on the air monitoring equipment. I'll help you put together your confined space safety plan if you feel it's weak. There's a lot of good information out there on the OSHA website to help you with that. The key thing on this is just, being safe. It's scary to think the conditions that were being created in the crawl spaces where we were using this particular spray glue. Again, thank God that someone did testing and found it. We probably could have easily killed someone if we hadn't been paying attention to this. So, yeah, anything you need from us as far as this, let me know. If you need help putting your plan together, reach out to me. Getting monitoring equipment, if you're confused, you have questions, give me a call. I've actually spoke with some OSHA people in Utah from the Utah OSHA. They're actually OSHA inspectors. I got some insight from them that I'm happy to share with you guys about the confined space safety plan and what you might expect. The key thing, the most important thing I took from all my discussions with the OSHA guys from Utah and from federal OSHA guys is have a plan in writing. If you've got a plan in writing that addresses these things and something bad happens, you're okay because you've got a plan in writing. If you don't have a plan in writing and something bad happens, you're screwed. That's where you really get in trouble. So make sure you've got a plan in writing, make sure that all of your employees understand the plan, and make sure that you're implementing the plan. Then you'll be fine.
Perfect. Does anybody have any comments or questions on that before we move on? All right, I'm hearing nothing, so the next couple items, I just wanted to make sure, especially for coordinators, that you guys know. So the monitoring of each of your program, I'm coming out and doing energy auditor monitoring. Wade and Dalton are coming out. Sometimes we're out at the same time, sometimes we're not. They're coming out and doing QCI and some production monitoring. And then if there are any corrective actions required, then, typically we give you a 30-day period. Brad is waiting before he comes out to do his monitoring. His monitoring will be your inventory, your finances, kind of programmatic stuff. He's waiting until after that 30-day period is over, after you guys have had a chance to make any corrections, before he'll come out. So his monitoring schedule, although he put out a tentative schedule, it is not set. So anyway, if you are trying to schedule that or have any questions about that, reach out to Brad directly as it gets close to your monitoring time to find out, specifically when he'll be there. And I think he's been pretty good about sending a pre-monitoring letter, but I think we had one instance where the agency was expecting him to show up and he didn't show because we were still in the middle of corrective actions. So just an FYI on that. Also, Brad wanted everybody to know that he meets monthly with our DOE project officer, and they discuss all kinds of things. So if you ever have questions that you would like him to consider, making part of that monthly meeting, and maybe find something out from DOE, he just said you're welcome to send him any topics for that meeting that he has. So if you have anything, send him an email. Last thing here, smaller items before we get to the main topic was I just wanted to take a minute and talk about drip legs, gas valves, and flex lines. This is important for every one of you to understand what's going on with this. The drip legs, gas valves, and flex lines has been on our health and safety checklist for a few years now. But as we have seen what you guys are doing in the field, and then as we have basically gained a deeper understanding of what it is that DOE wants or will allow or will not allow when it comes to health and safety items, we've realized that the the drip legs, the gas valves, and the flex lines on water heaters most of the time are not allowed based on the way we have our have our audits set up, and based on the way we told DOE we were auditing stuff. This will probably make a little more sense to the auditors, but I want to make sure that QCIs know and understand this as well. And when an auditor is auditing a measure, say they've come across an incidental repair measure, like they're going to add some insulation in an attic, but there's a little bit of roof repair. Maybe there's a little leak around a swamp cooler or something going on. They can write up an incidental repair, and when they write that up, they have to explain how that repair is directly connected or it's incidental to an energy conservation measure. So if an auditor was going to write an incidental repair measure to fix a leak on the roof, they would write in the comments section that this repair is incidental to, and the energy conservation measure could be, some attic insulation. So they would say this repair is incidental to attic insulation. And now that's part of justifying why you're doing that as an incidental repair. So basically they have to have a nice dark black line that connects that incidental repair directly to an energy conservation measure. Well, DOE has basically made that same exact connection with all of their health and safety measures. And I've been working with the auditors to try and understand this better. And in fact, I think I cut and paste some of the DOE has a draft health and safety plan that they've closed the comment period on. We're waiting to see what actually comes out of it. I did not notice any comments based on this, so I'm anticipating that they're going to release it exactly the way they wrote it. But what they wrote into their draft is it says that since health and safety measures must meet the definition provided in this guidance, and then they say which is I think it's down here. Let me just read it. So since health and safety measures must meet the definition provided in this guidance, the purpose of performing specific health and safety measures as they relate to energy conservation work being necessary because of or in order to perform weatherization must clearly be stated in the client file. All that mumbo jumbo, maybe I've taken it a little out of context or haven't got enough context here so you can understand what's going on, but basically what they're saying is that if you're going to do a health and safety measure, you have to clearly state why it was necessary because of or in order to perform weatherization. So essentially what they're saying is you have to say why you have to do this, and what that'll probably look like for Utah is that you will, anytime you auditors write a health and safety measure, you'll do the exact same thing for an incidental repair. You'll say this health and safety measure is incidental to this specific energy conservation measure. So how that relates to water heaters is if we're not doing any energy conservation measure on a water heater because we don't do energy conservation measure on water heaters, then we're not allowed to do health and safety measures that would only be warranted by an energy conservation measure on a water heater. So like a gas valve, a drip leg, or a flex line typically is not going to be directly related to an energy conservation measure. Every once in a while you could have one where if you had a leaky gas valve, then that could be directly related to your infiltration reduction that you're going to do in the house. So if you tighten up that house and there's a gas leak, now you have a direct relation. So now auditors can write that and say, hey, that gas valve is leaking and it's directly associated with the fact that we're going to tighten up the house. So we need to address that. But just because a water heater does not have a drip leg or it does not have a shut-off valve on it, it doesn't directly relate to an energy conservation measure that we're doing in the home. And so therefore, basically, most of the time, we shouldn't be doing them at all. So like the drip leg guidance is stop replacing drip legs on water heaters and furnaces as health and safety measures. And then we will probably remove this from the health and safety assessment. I'm on the fence on that one because I think it's good to indicate that. It doesn't necessarily mean you're going to do something about it. But so I'd be looking to the auditors for some guidance on that. And then we should only be replacing shutoff valves, flex lines as health and safety measures when they're leaking. And we should only be adding drip legs, shutoff valves, and flex lines as part of a new install when we have to bring that new install up to code. So these things can go in every time you have to install a furnace, if that's what your local codes require, which usually that is. And then same thing with a water heater. If you end up having to replace the water heater because of a venting issue, you're replacing the whole thing, then you can, you typically have to bring the rest of those things up to code, and so that all of those things would be included in the cost of installing that water heater. So I hope that will help, especially the guys that are out in the field and the QCIs, to have a little bit better understanding of why some jobs the auditors are calling for these things on them, and some of them they are not. It's because in order to justify spending the money, we have to have a direct connection to an energy conservation measure. I realize that was a lot. Does anybody have questions or concerns about that?
And what about protecting the employees if it's a health and safety issue because the employee could get hurt working on something?
Yes, and that is exactly, so a health and safety measure is allowable energy-related actions are those that are necessary to maintain the physical well-being of both the occupants and the weatherization workers, and this is the key, where actions must be taken to effectively perform weatherization work, or the actions are necessary as a result of the work. So give me an example of where you wouldn't necessarily be able to tie this back to an energy conservation measure, but your weatherization workers would be in peril or their safety could be an issue.
Well, I don't know. I guess you could tie most of it back, but like if there's a stair hazard or something that just going into the basement or going into the house itself.
Yeah, and all of those things, like anytime you run into an issue like that, that is a legitimate health and safety issue. There was a home where I saw the electric panel, the door or the cover to the electric panel was missing. And they were working right next to it. I could tell from the photos that I think the furnace was right next to the electric panel and they were going to be working in that vicinity. And the auditor wrote in there, we need a health and safety measure to put a panel cover on there. That kind of stuff is perfectly legitimate. That's exactly what DOE wants us to be doing as health and safety measures. I think the drip leg is the perfect extreme example because I can't think of a scenario where anybody's going to get hurt because there's no drip leg. And I think that's the point, is that somehow we put this onto a form and this is kind of made its way into the program as every time we see an appliance without a drip leg, we put one on it and we call it health and safety. And the point is that it's really not a legitimate health and safety issue. And so please stop installing them. Please stop calling for them on your audits. If you have any questions about them, auditors call me. And then, if you guys in the field have questions about them, you're welcome to call me. We can have discussions, or, if you just have other weird situations or scenarios that come up, reach out to us. But I think most of those will be kind of anomalies. I think for the most part, we need to stop installing these unless they're directly related to an energy conservation measure. Does that make sense?
Yeah, on the drip legs, but another one, we just had a water heater that had an extremely high CO up in the 1,000 range, and that used to be a health and safety measure. Is that still health and safety because you're not really tying it to anything?
Well, when it comes to that, I like to tell the auditors we want to have a nice dark line here. There's a couple of instances where that line gets a little bit gray. But we've written those right on our health and safety table, and one of the issues on the health and safety table is venting, and then the other one, if I'm not mistaken, is if you have high CO or if you're burning outside of the approved ranges. So
correct. Our guidelines specifically say if CO is over the acceptable limits, consider replacement of the appliance.
Yeah.
If it can't be corrected by doing a tune-up, and in those cases where you have a water heater that's well over 1,000 parts per million, chances that you're going to fix that are slim to none. Our guidelines allow you to replace it.
Yeah, we've tried to make a table where there's a bunch of stuff listed, and I've found more and more that we want to make sure if something's a little gray here, we want to make sure that that's on the table. So you'll still be allowed to do that. Make sure you're looking at that table. This is really just a good rule of thumb. Like if you're kind of thinking through a scenario, this is where you can start, but then go to the table. But we've written right on the table that that's not necessarily a prescriptive list of every single thing that you'll run into. So if you'll kind of use this and the table as a guideline, most of the time you'll be able to determine very clearly whether or not it's a legitimate health and safety item. If you've got questions, I'm happy to chat about it and see if I can give you any guidance on it. So anyway, unless anybody has any other questions on that, let's move on to our main training here. And if you do have questions or want to talk more about it, we can definitely call me, or if we need to, we can discuss it at one of our next meetings as well. So, all right, Wade, you're up, man.
Okay. Do you have to share your screen with me, or?
Oh, I can make you the.
I
think I can make you the person, can't I?
Yeah, I think so.
Let's see.
Give us a minute, guys, while we figure out how to swap computers.
If I'm smart enough to do this, let's find Wade. And okay, I think I sent it to you.
All right, can you guys see my screen now?
I can see your screen.
Got a bunch of purple stuff on it.
Yep, we see it.
Okay, let's see if we can. Okay, can you see that PowerPoint presentation right now?
Yep.
Okay, so let's go ahead. All right, do you guys see just the PowerPoint presentation without the notes? See
Yeah.
the little circle at top, little gene thing?
That's what I'm seeing. I'm not seeing any notes.
I got too many screens to look at, so I got to make sure we're looking at the right one. All right, so basically, because it is heating season, we've decided to do a little bit of training on combustion analysis. I can already promise you we're going to go over time, guys. I apologize. This combustion analysis class was originally 200 and something slides. I've whittled it down to 32 slides. So if I spend 1 minute on each slide, we'll be done in 32 minutes. So I apologize, we will go over. I've tried to make this kind of just a basic class and based off of some of the stuff we've seen in monitoring. So we're going to discuss some basic things, how to properly do it, and give you a little bit of information on what all those numbers mean. Because some of the things we've seen in monitoring is, of course, guys doing combustion analysis wrong, and it was just because they were trained wrong. Someone who didn't know what they were doing trained them how to do it, and that's all they knew. And the other thing I see is guys who know how to do it, but the thing that comes out on the printout, that means nothing to them. They don't know what they're looking at. They don't understand it. And again, that's just training. It's because no one's ever taken the time to really teach you about it. So we'll get a little bit into that today. So again, this is just going to be a refresher class on combustion analysis. Please ask questions as we go along if you have any. So what I want to start with is asking you guys this question. Looking at those two flames, and this is a drum heat exchanger looking from the top down, can anyone tell me out there which one of these flames is the better burning flame? Left one or the right one? Don't all answer at once.
Left?
Left? Some of you are saying left?
That's my guess.
Okay. Well, the thing here is that it's impossible to tell by looking at the flame, okay? there are some clues here that we can see. One of the clues we can see is on this left flame. You see these hot spots on the back wall of the drum? Those hot spots are caused by unburned fuel moving through the combustion process, and that unburned fuel hits the back of that heat exchanger and burns off right there. Okay? That's actually a problem. But at the end of the day, the point I'm trying to make is there isn't anyone in the world who can look at these flames and tell you which one is actually the better flame. There are some subtle clues that if you know what you're looking at, yeah, you can kind of get a good idea. But even looking at this, there isn't a person alive who can tell you which one of these flames is producing the most amount of carbon monoxide, which at the end of the day is one of the key things we're looking at. The only way you can make that determination is through testing. And that's why we do combustion analysis and testing, because you can't look at a flame and say, oh yeah, that flame's good, everything's okay. We have to test. Okay? So basically, combustion analysis, guys, is nothing more than evaluating the air and fuel mixture of an appliance. And an incorrect air-fuel mixture will cause the appliance to become inefficient and also potentially dangerous. So in order to have combustion, we have to have three things. We have to have air, we have to have fuel, and we have to have an ignition source. And if any one of those three components are missing, we'll never have combustion. Okay? So we have those three items for combustion, but we also have to have those mixed properly. We have to have the proper ratio in order to get the correct combustion. So here's an example using natural gas, and we have a 1 cubic foot box. So this box has 1 cubic foot of air in it. And if I take this 1 cubic foot box and I put 3% gas in here, 3% natural gas. So in this box is 3% natural gas and 97% air, and I try to ignite it, nothing will happen because there's not enough fuel. I haven't reached my lower explosive limit yet. Okay? Now let's look at the other end of the spectrum. Let's say that I take this box and I put 16% natural gas in it and 84% air, and I try to ignite it. Nothing's going to happen. Now I've got way too much fuel in the mix. Okay? I'm above my upper explosive limit. So natural gas has a very narrow window of how it burns properly. And the sweet spot is right here in the middle. To have really good combustion with natural gas, ideally, we want this 1 cubic foot box to have 10% gas and 90% air. Then we're right in the sweet spot. But you can see we go this direction, we start to lean out. And as we lean out, we'll have problems. We go this direction, we'll start to get too rich, and we'll have problems. Okay, so one of the key things about combustion analysis is understanding our air-fuel ratio. And that is what makes our appliance burn properly and efficiently. So one of the things we saw in our monitoring was guys not understanding proper probe placement, and that's critical when you're doing combustion analysis. You have to take the samples in the correct spot, otherwise you're going to get incorrect readings. And the correct spot is always in undiluted flue gases. So what the hell do we mean by undiluted flue gases? Well, let's start with water heaters, because in our monitoring, this is one of the appliances that we saw there was a problem with guys doing combustion analysis. So here we have a water heater, here's the burner, here's what they call the fire tube and the turbulator. Your undiluted flue samples or undiluted gas samples will always be down inside here. This little component right up on top here is called a draft diverter or draft, and it allows dilution air to enter into the flue. So if you're taking your combustion analysis up here, you have a diluted sample. That means there's excess air and stuff mixed in it. You're not getting a true sample of what's going on at this burner. In order to get that, we need to be down inside of here. So here's a real good close-up. Again, here's a water heater draft hood. You can see my probe right here. The probe is going down into the fire tube or the turbulator area. If you take your reading anywhere above this line right here, you're going to have excess air because, again, the draft hood's job is to allow air from the room to enter into the flue. So all this air from the room is going up into that flue. Okay? And that'll give you a skewed reading. you're going to see high O2, high excess air, and low CO production. In fact, in some cases, your O2 will be over 17%, and most every combustion analyzer out there won't even start doing math and giving you readings until the O2 drops below 17%. So again, we've got to be down in undiluted flue gases. So here's how they did this. They just simply drilled a hole here and angled the probe and got it down in there. You can drill a hole in the draft hood, stick your probe through there. Sometimes you can get your probe under the draft hood and get it in there. Okay, but one thing I want you to notice is this, and I'm sorry this picture's a little blurry. The CO in the undiluted flue sample is 20 parts per million. Now let's go to the diluted. Now we put our probe in the wrong place. We can see we're above the draft hood. Now we've got all this dilution air entering the process. And look what my CO did. The reading is dropped by over 50%. Okay, so we're getting a skewed reading. What is really going on with that burner is down here. Okay, so probe placement is critical. This is one thing we saw in our monitoring that guys didn't understand that. Our draft reading would be taken up here somewhere to get our draft, but for combustion analysis, we've got to be down here below this draft hood, because the job of the draft hood is to allow tons of excess air to enter this flue. It helps keep the flue dry, it prevents the flue gases from condensing, and it adds volume to the flue so that the flue can actually vent. That's what dilution air does. Okay? So another type of draft hood you might run into out in the field is this. This is called the bell-shaped draft hood, and they're very common on boilers. But you basically have a pipe here, and then this bell-shaped looking deal, and then the pipe continues. If you run into this, you need to be taking your sample before the draft hood, because again, this draft hood is allowing air to enter and mix in this flue right through this area here. So we need to make sure we're taking it down here. I've seen guys try to test them up here because they just simply didn't understand what the function of this thing was. It's just another type of draft hood that allows outside air to mix with the flue to help it vent and stay dry. Okay? Draft test, of course, we would do above it. Combustion we do below. Okay, this is a mid-efficient furnace. So this is any furnace that's 78 to 89% efficient. Proper probe placement for combustion analysis is within 18 inches of what we call the breech. Okay, so this is the inducer motor, and this point right here where the inducer motor connects to the flue is what we call in the industry the breech. So we want to be up above the breech, somewhere around 18 inches. Okay, maybe pick right in the middle or at the top or whatever, but this is the best place to do a combustion analysis on a mid-efficient furnace, about 18 inches above the breech. Okay, of course, on high-efficient furnaces, high-efficient is anything over 90%. We can drill a hole in the flue. We want to be in a vertical piece of flue, not a horizontal piece of flue. Does anyone know why we wouldn't want to drill in a hole in the horizontal piece?
They have water in them.
Because these flues are full of water, right? And if we drill a hole in a horizontal piece of flue, we could probably make a place to trap water and have a better chance of condensation leaking out of the flue. So if we do it in a vertical piece, we reduce that possibility. You can also go to the termination of the flue. That's a great place to do it also, is at the termination. Okay? And on these flues, we need to make certain that we plug the hole, because high-efficient furnace flues, or furnaces with PVC flues, this flue is under positive pressure. This inducer motor is now actually pressurizing this pipe and forcing the flue gases out. If we leave an open hole in it, flue gases and water vapor are going into the home. On water heaters and mid-efficient furnaces, I personally don't care if you plug the hole or not. That being said, sometimes people freak out if you drill a hole in their flue and don't put a plug in it, so probably a best practice is just plug them. But at the end of the day, if you don't plug those holes, nothing bad's going to happen. Okay? They're negative pressure flues. When they're working right, they'll suck air into the hole. These ones are different. They're positive pressure. We absolutely have to close that hole off. Okay? Here's another one that I found a lot of guys didn't understand. This is a low efficient furnace. We also call them 60%ers or standing pilot furnaces. We probably don't test them a lot because we just kind of shoot them on site. But I found that guys have been trying to test these up here in the flue when they were testing them. The problem is this component right here on these furnaces is the draft diverter or the draft hood. So here's how it works. There's burners on here. So there's 4 burners, and sorry I don't have a better view of the burners, but there's 1, 2, 3, 4 burners. Same over here, 1, 2, 3, 4. The exhaust gases come out of each individual burner and mix in the draft hood with the dilution air and then enter the flue. So if I take and put my combustion probe right there where the red pointer is, I now have a diluted sample, do I not? I've got a ton of dilution air in there. If you're testing these types of furnaces, your probe needs to go into each individual heat exchanger. So I'd test this one, document it. Test this one, document it. This one, document it. This one, and document it. And then you just look for the problem one. So let's pretend that this is 400 parts per million and the other 3 were 20. Well, that's a problem, okay? Don't add the numbers and take the average. The problem is you got one of these burners that's screwed up. It's 400 parts per million. That's a condemnable furnace, okay? So anyway, this is just another thing I found that, you know, guys just didn't know. They're up here in the flue, but when you have this big draft hood or draft diverter and you're going to test these furnaces, get into each exhaust port. And you can stick your probe right up through there and get it right into each exhaust port.
Hey Wade, on that one, do you average them when you're done, or do you want to report and kind of put in your file the CO from each burner?
You would just take the CO from each burner, and again, I'd go back to my example. If we measured all 4 of these, and let's pretend that this one was 400 parts per million, and the other 3 were 20, 15, and 10, we have a problem. Document them all, but your problem is right here. I've got a burner producing 400 parts per million. That's a problem, and we could condemn this furnace. We should condemn this furnace if we can't fix that based on the CO being produced by that one burner. There's no reason to add them together and average them. This is an actual CO reading from each burner, okay? Our high-efficient and mid-efficient furnaces, all of those burner gases mix together, okay? But here they don't mix until they get in with the dilution air, and if we measure here, we have a diluted sample that's not a real representation of what's going on in each of those burners. Does that make sense?
Thank you.
You're welcome. So, does anyone have any questions on probe placement? It's pretty rudimentary, but because we saw some issues with it in our monitoring, I wanted to talk about it and make sure you all understand it. So, any questions before I move on? Okie doke. So now that you know where to put the probe, you push the print button and this tape comes out with all these numbers on it. So what the hell do these numbers mean to anybody, okay? Well, that's one thing we saw in the field. That, yeah, guys knew where to put the probe, and then they push print, and I ask them about the tape, and they just go, I don't know, no one's ever told me what any of that means. So we're going to go over and just give you some basics. This stuff gets pretty in-depth. And when we're all done, I will actually give you some reference, or if you want to take the initiative and learn more yourself, you can. But in order to understand these numbers and what's going on, I've got to discuss a little bit of science, okay? So bear with me. So one of the things that we need to know is what our air is actually comprised of, okay? So this is the Earth's atmosphere, and the air that we breathe is 20.95% oxygen. And let's just call it 1% to keep the math easy. The rest of the air we breathe is nitrogen. There's a ton of nitrogen in our air, okay? And then there's some other trace elements, argon and carbon dioxide. We need to understand this relationship because we have this thing in combustion analysis called excess air. And when you have excess air, you have a lot of nitrogen in the process. And we'll talk about how that affects the process. But the air we breathe is only 21% oxygen. The rest is other stuff, okay? Nitrogen being the biggest amount of stuff. And have you guys ever wondered when you turn on your combustion analyzer what this number right here means? That's your combustion analyzer measuring the amount of oxygen in the air you're breathing. Okay? Look at that, 20.9, 20.9. So when you turn your combustion analyzer on, it has some sensors in there that start taking oxygen readings. And it should always be about 20.9. And just FYI, at levels below 19.5%, human beings will start to have problems functioning normally. And at levels below 6%, you'll die immediately. Death is immediate. Okay? So this, when you turn it on, is just telling you, hey, you're in the atmosphere. There's 20.9% oxygen in the air that this machine is sampling. Okay? So again, we just need to emphasize the air that we breathe is the air that we're using for combustion. Okay? In order to have combustion, we have to have air, fuel, and ignition. So the air we're using, again, 21% oxygen and the rest is nitrogen. So again, how does that all play out? Well, nitrogen, basically, I mean, we say in the combustion world that it does nothing to the combustion process. And that's sort of true. It does nothing to help the fuel burns. Nitrogen will pass through the combustion process unchanged. And we'll talk about that a little bit more. But it does have some problems. Nitrogen loves to absorb heat. Okay? It'll suck up a lot of heat out of the system. So if we have a lot of excess air, or nitrogen by default, it'll start to reduce the flame temperature dramatically. A good example of this is natural gas, when burned in any combustion appliance in the Earth's atmosphere, will have a flame temperature of about 3,500 degrees. If you could take that same natural gas and burn it in 100% oxygen with no nitrogen in the mix, your flame temperature will be well over 5,000 degrees. That's the effect that nitrogen has on the system. And so we have to be aware of that fact because we deal with this thing called excess air. Okay? Nitrogen increases the volume of the flue gases. It reduces the efficiency of the combustion process. And at high flame temperatures, you'll start to form these things called nitric oxides and nitrogen dioxides, which are poisonous greenhouse gases, basically. So that's why I brought this up. We've got to be aware of what's going into the combustion process in order to understand what comes out of the other end. And of course, we've got to understand how the combustion process works. So this is a typical burner that you would find in any furnace and in a lot of water heaters nowadays. So what we have is we have gas, or methane, which is natural gas, which is the CH4, being shot into the burner. And as it's being shot in, it creates a Venturi effect. And primary air is sucked into the burner, and that's all mixed together. So remember, we have to have an air-fuel mixture. And the manufacturers build these so that hopefully the amount of gas and air is right at that sweet spot. And then it comes out here and we have some sort of ignition source and we light it. But we also have this extra air that surrounds the flame, and this is what we call secondary and excess air. And this is built into all combustion appliances as a safety factor. Okay? There's no way that we can get perfect combustion unless we're in a laboratory, but we can get complete combustion by adding extra air, and we just need that extra air to burn to make sure that that fuel that's in there is burned off. And this is built into the systems because what if these burners get dirty back here and it can't get the correct amount of primary air in? It has a redundancy factor. Okay, I'm short on primary air, but I can get some more air out here on the other end to ensure that all my fuel burns off so that we get complete combustion. Okay? The thing we don't want is incomplete combustion. And that's kind of what we're going to talk about next a little bit here. And here's where we get a little science-y, you guys, so bear with me. This is the actual combustion process, and we've broken it down to a molecular level. So over here I've got my natural gas. Okay? Natural gas is CH4, carbon and hydrogen. I got one carbon, 4 hydrogens. Over here I've got some packets of air. Okay? Remember, my air is oxygen and nitrogen. So here's one packet of air. Here's another packet of air. And here's another packet of air. Okay? I'm going to throw that into the combustion process. I'm going to chemically change it by igniting it. And out of the other end, everything that goes in has got to come out. Now hopefully it comes out the right way. This is the way we want it to come out. I'm going to have carbon dioxide. So my carbon is going to mix with one of my oxygen molecules and create carbon dioxide, CO2. The other thing that's going to come out is my hydrogen. So I've got a hydrogen. Two of those hydrogens mix with an oxygen. I got H2O, which is just simply water. Okay? You can see all my components are being accounted for. The carbon mixed with one oxygen, two hydrogens mixed with part of this O2, two more hydrogens mixed with part of that O2. So we have carbon dioxide and H2O. What does my nitrogen do? It just bounces through the process, unchanged. And here's my excess air. Okay, I got some extra air in the mix just as a precautionary matter. This is what we want to see. This is what our combustion analyzers measure for us. Carbon dioxide, excess air, how much oxygen's left over. The problem we run into is when we start getting this. So now look what I've done. I've got the same natural gas, but I reduced my air by 2/3. Okay? Now let's look at the combustion process. We run it through, so I still recreate some H2O, some water, but now I've got these unburned hydrogen molecules, and that's what we call soot. Okay? There's not enough oxygen for these guys here to combine to create more water. They're just kind of passed through unburnt. Nothing's happened to them. This is soot. And the other thing we've started to create now is this combination. Carbon with one oxygen, okay? Because I've only got two oxygens here, O2. One of them matched up with a hydrogen, the other one matched up with the carbon and created CO, carbon monoxide. So now I've got soot and carbon monoxide. And look what's missing, okay? I don't have my excess air anymore. The reason my excess air is non-existent or low is because I started with insufficient air, okay? My nitrogen passed through unchanged, but here's the part that we worry about. Now we've got soot and carbon monoxide moving through the process, and that's what we want to avoid, okay? So hopefully that helps you gain a basic understanding of the combustion process and what's going on, but we're measuring the stuff that comes out this other end. Any questions on that before I move along? All right, hopefully I'm not boring you too bad. So here's where we get into what do all those numbers mean, okay? So let's start with these three things I've highlighted. Oxygen, O2, CO2, carbon dioxide, and excess air. These guys all work together, okay? They're inversely proportional, which simply means if one changes, the others will change. So if I increase my O2, my CO2 will decrease, inversely proportional. As this goes up, this goes down. If I increase my CO2, my O2 goes down. And O2 and excess air will always go the same direction. It just makes sense. If I'm putting more air into the mix, I've got more leftover oxygen and more leftover excess air. Okay, so that's kind of a thing that we need to understand how those work. They're inversely proportional. As oxygen increases, excess air will follow it every time. As oxygen decreases, excess air will follow it. And carbon dioxide does exactly the opposite, okay? So for every action, there is a reaction. So we're going to go through a few of these here. And again, remember, guys, all we're doing is adjusting the air-fuel mixture. There's only two things that we can change, air and fuel, okay? But it's amazing the effect it can have. So let's start with a decrease in the supplied air to the combustion process. Well, if I have less going in, it makes sense there's going to be less coming out, right? Less O2 measured in the flue gas. Remember that CO2 and O2 are inversely proportional, so higher CO, and this condition may result in incomplete combustion, forming carbon monoxide due to a lack of air to mix with the fuel. If I don't have enough air in the mix, I have the potential to have unburnt fuel. Okay, so remember the molecules I showed you. I've got unburnt hydrogen coming out. I've got carbon mixing with oxygen to create carbon monoxide. Well, let's put too much air in the mix now. So I'm going to increase the air supply to the process. Well, if I have more air going in, it stands to reason I'm going to measure more O2 coming out, correct? And of course, my carbon dioxide, being inversely proportional, is going to go down. and this may result in incomplete combustion forming carbon monoxide due to cooling of the flame. Remember when we talked about all that extra nitrogen that's in the air? All that extra nitrogen cools the flame, and if I've got a lot of excess air in the mix, I'm going to start cooling my flame, and if I cool my flame, it starts screwing up my combustion process, and now I've got unburned hydrocarbons moving through the process, creating CO and soot. So that was discussing what we can do to the air. We can either increase or decrease the air. The only other thing we can change is the fuel. So let's take a look at our fuel. So let's increase the fuel pressure or add more fuel to the mix. Okay? When we do this, we can increase the fuel velocity, and that can cause what we call flame liftoff. We can actually blow the flames right off the burners because the gas is coming through so fast and so hard. Of course, if I've got more fuel, remember guys, I've only got two things I can control, air and fuel. If I add more fuel to the mix, my O2 is going to drop, right? That makes sense. There's only two things I can control. Carbon dioxide's inversely proportional. And again, because I have more fuel, there's a lack of air because I've increased the fuel so much, and I can form carbon monoxide. Let's go to the other end. Let's just reduce the fuel pressure. So if I decrease in air-fuel velocity, you can get what's called flashback or rollout because the gas is moving so slow through the burner, it'll flash back or roll out of that burner. And of course, because there's less gas, I'm going to see higher O2. Okay, stands to reason. Remember, I've only got two things I can control, air and fuel. CO is inversely proportional. And again, we can have incomplete combustion with carbon monoxide due to cooling of the flame with too much excess air. Okay? So that's what those numbers are telling you. And you can affect your O2 and your excess air simply by changing your fuel. Can anyone think of other ways that you can affect the amount of air that goes into the combustion process on an appliance? Okay. Well, let's think about a water heater. So let's say we take a water heater and we put a blanket on it and we accidentally cover the intake vents. Is that going to reduce the amount of air available for that appliance to burn? Absolutely. Okay. So that's another example. There's lots of others out there. We'll move along and get you guys through this. So the other thing we see on the tape is the CO, carbon monoxide. So we have CO as measured, which is this reading right here. This is the measurement that the machine actually measures with its carbon monoxide sensor. Then we also have another one that's called air-free. Okay? This is an area where I've seen guys get really confused. This is the actual CO reading as measured from the machine. Remember, oxygen moved through the process. So we have oxygen and excess air, which dilutes CO. So this reading is the diluted reading of CO production because there's still oxygen left in the mix coming out of the other end, and there's still excess air left in the mix. This down here is called CO air-free, or in the case of this particular instrument, CO reference O2 0, which means I've asked the machine in this box, tell me what the CO is with all of the O2 removed. The machine does math to figure that out. There's actually a formula you can do by hand. I was going to put it on here and go through it, but we don't have time for it. I can tell this machine to tell me what is the CO with 10% of the air left in, or 20%, or 30%, or 50%, whatever I want. If this was 100%, this number would be the same as this, because that's what this is measuring, is the CO as measured with all of the O2 and excess air in the mix. I've asked this machine to give me the air-free measurement, because that's one of the measurements that the industry uses. This reading will always be higher than this reading, and in this case you can see by almost 50%, because the oxygen and excess air dilutes carbon monoxide. I've asked the machine to tell me my O2, pretend it's 0, what is my reading? 16 parts per million is the true CO production for this piece of equipment. The ongoing debate is, which one do we use? Which one decides our decisions? Well, since I've been in the program, we've been kind of working with this one, as measured. I've had people in our program even, and outside our program, say, nope, you need to be using this one. At the end of the day, I guess my stance is I don't care which one we use. The industry's moving to this one, BPI is moving to this one. This just means that you're going to condemn more equipment because you'll always have air-free as a higher reading than this reading. For now, I guess, we're looking at this number, and I'm fine with that. In the future, we will probably be forced to shift to using only this number. But you need to understand what they're both telling you, okay? This one doesn't take the oxygen out of the equation. This is as measured in the flue. This one does math and says, if there was no oxygen left, here's what we're actually measuring. By the way, ambient CO measurements, the ones we take in the air, are always this, as measured. We never use air-free for ambient CO measurements. Any questions on that before I move along? All right. So just to recap, CO is measured in parts per million. As measured is a term used to describe CO actually measured by a CO sensor. Air-free is a calculation based on the as measured CO and the percentage of O2 in the flue gases. If anyone wants to geek out on the table to use the math, let me know. I'll send you the table. You can figure this out all with mathematical formulas. CO air-free is a unit of measure designed to compensate for excess O2 in the flue gases that dilutes the as-measured CO measurement. CO air-free is only used when testing flue gases. When we test ambient CO, it's always as measured. So here's some other information that the tape gives you. This is called efficiency. So EFF is efficiency total, and then this one also tells me loss. These two numbers will always equal 100%. So this is telling me that this water heater is at 82.8% efficient, or I'm sorry, this was an 80% furnace, not a water heater. So 82.8% of the gas it's burning is being used for heating the house, and 17.2% of it is lost out of the flue, or wasted, okay? This number should closely match the rating of the furnace. So for example, if you can find the sticker on the furnace that has the AFU rating, the annual fuel utilization efficiency. In this case, the furnace had an AFU of 80%. This number should be within a couple of percentage points of what it's rated at, okay? So it was at 82.8. It's right where it should be. And by the way, auditors, if you have a furnace and you can't find the efficiency of it, so you can't find it in the Preston's guide because all the model and serial numbers are missing or whatever, you can use this number. This is the AFU rating of a furnace, the annual fuel utilization efficiency. So if on this particular furnace, I didn't know what its efficiency was because I couldn't find it anywhere, I can take this number and put it into the NEAT input tool and say, yep, this furnace is 82% efficient. And that is a very accurate number, okay? Any questions on efficiency and loss before I move along? All right. Okay, this is the flue or stack temperature. So our combustion analyzer will measure the temperature of the flue. And that's what this guy is right here. There's an actual temperature sensor in the probe. And on water heaters and mid-efficient furnaces, this should be between 300 and 500 degrees when that equipment is up to full operating temperature. I've seen too many tapes on water heaters where this number was like 125. That tells me that they took their reading immediately at startup. They didn't wait for it to warm up a little bit, okay? That's easy to pick out. And lo and behold, when I see that, I see these other numbers skewed too. So water heaters and mid-efficient furnaces and atmospheric boilers, this number will be between 300 and 500 degrees when that thing is up to operating temperature. On 90% furnaces, it should never be over 140, and you can see it as low as 90 degrees. Okay, that's no big deal. Okay. This is the temperature of the air used for combustion, or the air around my combustion analyzer. My combustion analyzer is in the same room as the furnace when I did this, and so the air that that furnace is using, because it's an 80% and it takes its air for combustion from the room it's in, Okay, well 71 degrees. This is just called the delta temperature. It's just this number minus this, and it gives you that. Why do some combustion analyzers give you this information? Because on big commercial jobs, some manufacturers require you to set them up with a delta temperature of X, Y, or Z. For what we do in residential stuff, this is nothing you ever need to worry about. But this is important, and this is important too. And talking about that, here's another thing I found that a lot of guys were uncertain on. So this is my combustion analyzer. Over here is the temperature probe that goes out into the probe I stick in the flue. This gives me my flue temperature. Over here on every combustion analyzer is another, they call it a type K thermocouple, that I can put a temperature probe in. If this probe is not in this slot, then the machine just reads the temperature of the air around it. Okay? So if this machine is in my office and my office is 68 degrees and this is not plugged in, this machine is going to say, yeah, the air around me is 68 degrees. And that's all good and fine if you're doing readings on furnaces that are pulling their combustion air from the same room the furnace is in. Okay? Water heaters, 80% furnaces. But when I get into high efficient furnaces that have two pipes, one pipe being the flue or the exhaust and the other one being the intake, if I'm standing in the house and the house is 68 degrees, but the outdoor air is 0, there's a large temperature difference there, is there not? And this probe needs to be used, and this guy inserted into the combustion air pipe. You drill an 1/8 of an inch hole in the combustion air intake and put this in, because the machine, in order to do accurate math about efficiencies and stuff, has to have accurate input. It needs to know, what is my intake air temperature? If my furnace is pulling its intake air from the outside, and the outside is dramatically different in temperature than the inside, I need to get that reading so I get accurate numbers. Now, let's say that the inside is 70 and the outside is 65. Okay, I'm fine. You don't need to put that in. There's only a 5-degree temperature difference, and it's been my experience that's not going to cause a big change. The other thing you can do is just go out to the termination. On high-efficient direct vent appliances, if this machine is outside, then the air that that furnace is using for combustion is coming from the outside, and this machine will read the temperature of the air around it and give you accurate readings. But again, it's just a piece of information that I've discovered a lot of guys just didn't know. It's just because of no one ever taught them. Okay? So just bear that in mind. If there's a dramatic difference between where you're standing and the air that that equipment is using for combustion, you'll get more accurate results if you use this probe and take the temperature of the incoming air charge. Okay, we're almost done, guys. Only 5 more slides, and then we'll get you out of here. So again, the thing I want to emphasize here is complete combustion is possible. This is a tape from one of our monitorings, and this is a really good tape. And in fact, this particular appliance was producing high CO. The auditor called for a tune-up on it, and when they were all done, I mean, this is textbook. O2, 7.3%, CO2, 7.6, excess air, 54. The industry kind of says if this is at 7.5 and this is 7.6 and this is 50%, that's like the perfect sweet spot. And they got really close, but the key thing to take away from this is look at your CO production. As measured, 0. CO air-free, 0. This is complete combustion. There is no carbon monoxide in this. So it can be done. And this is a great tape. That's what we like to see. And if you want to take the initiative and learn more on your own, get this book and read it. This is a great book. Eric Rasmussen is the one who wrote it. I've been to a couple of his classes. The guy knows combustion analysis. You can go to escoinstitute.com and buy it for $45. It's a really good book if you want to learn more. So anyway, that's all I got. Do you guys have any questions? Is anyone even still there?
I'm still here, Wade. And that's been very, very helpful for me, who knows nothing about combustion.
It was a whirlwind thing. You know, anytime you guys have questions, that's what I'm here for. So if you got questions on combustion analysis, please call me. But hopefully that was informative and not too boring for you. If you want to know more, call me.
Thank you so much, Wade. I'm going to take, I've been recording this, so I'll send everybody a link to the whole meeting later today. But if you guys are looking for just that section of the video that Wade was talking, I'll cut that out and I'll post that on the IWTC website as one of our videos. That way, if you need to go back to it as you're kind of testing and learning, we'll use that as a resource until we have something better. But I felt like it was pretty good as a starter point. So the next meeting will just be the first Tuesday of December, which I think is the 6th. Yeah, the 6th. And probably just the same as last time. If anybody has any suggestions for topics, send them to me. Otherwise, we'll kind of talk amongst ourselves and pick something we feel is pertinent. Does anybody have anything that has been on their mind that they'd like to have discussed as a topic? All right. Well, does anybody have anything else we need to talk about before we end? Well, thank you guys for joining us, and thanks for sticking with us a little long to go through all this stuff that Wade had. Have a good day, guys.
Okay,
Thanks, guys.
Thank you.